Hey, in this video, I'd like to introduce you to a new concept. It is a version of energy, and this version of energy is called kinetic energy. So I'm going to introduce you to this idea of the kinetic energy, and then I'm going to calculate a few examples and have a few comments about these examples, especially in comparing with the notion of momentum. Momentum and kinetic energy, they seem like they're kind of saying the same thing, but actually they're very, very different. Okay, so kinetic energy, it is another way to summarize mass and motion. But very importantly, and I think this is very interesting, this thing called the kinetic energy is the right way to think about the concept of energy associated with objects with motion, right? So the reason I want to say that it's the right way is because if you think about, it's the right way. Here is what I mean by that. There is a complicated formula for how to calculate the kinetic energy. And it's not really complicated, but it's kind of complicated. So the way that you properly calculate and think about the energy associated with an object moving is you first take the mass, you multiply by the speed squared. You see this little 2 up here? You multiply by the speed squared, and then multiply all of that by 1/2. And this is the typical way you tend to see it in textbooks. So symbolically, what you're doing to calculate the kinetic energy, you're taking 1/2 of the mass times the velocity squared. So let me erase all those little orange things, right? So let's do some examples of calculating this kinetic energy. In order to do this, though, I'd like to introduce you to a new unit of energy. It is the International System Unit, the SI unit, and it's called the joule. And this is the symbol, capital J. So for example, we could talk about 20 joules of energy, or 500 joules of energy, or 10 to the -12th joules of energy, right? We can have big energies and small energies, right? The amount of energy associated with the kinetic energy of an atom could be really small. And then the amount of energy associated with the kinetic energy of, say, a moving rock or a moving pencil, it'd have to be moving quite fast, but that could be something like 20 joules, right? A moving planet Earth, we're talking about 10 to the 30th joules or something like that, 10 to the 40th joules. Okay, but this unit, the joule, has a very particular relationship to kilograms, which is mass, and meters per second, which is what's in the velocity. But the velocity in the kinetic energy formula is squared, so that means these units are going to get squared. And the SI definition of the joule is 1 mass unit times speed units squared. Another way to write the joule is equal to a kilogram meters squared per second squared. Okay, so you're going to see this arise naturally when we calculate a couple of example kinetic energies. So let's calculate the kinetic energy of this situation right here. So in this case, the kinetic energy is equal to 1/2, right? Mass times speed squared. So 1/2. The mass is 3 kilograms. And the speed is 2 meters per second. But we have to square it. And squaring it means that we put it in the equation twice multiplied, right? That's what squaring means. And so if you go through the motions, let's put all the numbers together. So some numbers we have are divide by 2, multiply by 3, multiply by 2, multiply by 2. And so if you do this out, right, 3 times 2 is 6, times 2 again is 12, divided by, or multiplied by 1/2 is again 6. So the number is 6, right? That's what 1/2 of 3 times 2 times 2 is. And then the units are kilograms, meters per second, that's from the first one, times meters per second, that's the second one, right? And so this all amounts to 6 kilograms meters squared per second squared, which we know is called the joule, right? 6 joules. So let's do this one next. It's in white. So instead of a 3 kilogram object, we have a slightly less massive object, 2 kilograms. And instead of moving at this slow speed, 2 meters per second, we have a slightly faster speed, 3 meters per second. So let's calculate the kinetic energy. A 2 kilogram object moving at 3 meters per second. Oops. So the kinetic energy is 1/2 the mass times the speed squared. So 1/2 the mass is 2 kilograms. And the speed is 3 meters per second. But remember, we have to multiply it twice because it's squared in the formula, right? This is the little 2. So when you do this calculation, 1/2 of 2 is 1, times 3 is 9. And the units are all the same, kilograms times meters per second times meters per second. That is called the joule. So I've got 9 joules of kinetic energy for the white object. And for the orange object, I have 6 joules. Right? So they have different kinetic energies. Check it out. I have more mass, but it's moving slow, than this case, which has a little bit less mass, but it's moving faster. If you look at how the kinetic energy formula works, it actually depends on both the mass and the speed, but did you notice that it depends on the speed sort of more than it depends on the mass? That is, it's more meaningful to have a faster speed for the size of the kinetic energy compared to having a certain amount of mass. Going faster with this smaller mass gives this large kinetic energy compared to moving somewhat slower with more material. You get 6 joules, slightly less kinetic energy. So up here I said that there was an interesting comparison to make with momentum. If you look at these two objects and think about momentum, remember momentum is just mass times velocity. First thing you'll notice about these two objects is they have opposite directions of motion, so they will have opposite momenta. So let me write this down. So they'll have opposite momentum directions, right? Remember, the direction of the motion is towards the right for the orange object. Direction of motion is towards the left for the white object. So right and left are opposites. So these two momentums are opposite in direction, but at the same time, I have 3 kilograms moving at 2 meters per second. That's 6 kilograms meters per second of momentum. And over here, I have 3 kilograms moving at, 3 meters per second of motion with 2 kilograms. This is also a momentum of 6 kilograms meters per second. Opposite momentum directions, but the same amount of momentum. So if we compare momentum with kinetic energy, we can see that even though the kinetic energies of two objects might be different, 6 joules, 9 joules, that doesn't necessarily mean that the amounts of momentum will be different, because that's 6 kilograms meters per second and 6 kilograms meters per second. Another thing is, kinetic energy is just a number. There is no direction. And what's more is kinetic energy is always bigger than or equal to 0. There is no negative kinetic energy. No such thing. Kinetic energy can't be negative. Momentum, though, momentum is a vector. So since momentum can be a vector, or is a vector, you can have, in a sense, negative amounts of momentum, right? You just have momentum, say, pointing left or down. We could call those negative. But kinetic energy, moving left, moving right, doesn't matter. Those are both considered positive kinetic energies, right? Kinetic energy cannot be negative. All right.